I wanted to watch movies while they downloaded, so I built my own live streaming version of BitTorrent. Let's check it out. SiddTorrent. Instead of downloading a movie file directly from a server to a user, BitTorrent works by having everyone upload and download at the same time. So, how does everyone know they are talking about the same file? It's all because of the .torrent file. This is our architecture. It's pretty simple. So we have a session or a API which basically calls the torrent parser, which calls a tracker which for peer discovery, which creates a peer handshake. Then we create a peer handshake. Then we go to a scheduler which schedules piece manager, choke manager, rate limiter. And after everything is done, after we get our pieces, we describe them and then we add it to the storage. So that's the intuition in a very layman language. Let's understand that more deeply. So a torrent file looks like this. For us, the most important part is the info dictionary. Okay. So info dictionary, which contains the name, total length, piece length, and the pieces themselves. So why divide it into pieces? It allows multiple peers to work simultaneously. Every piece gets hashed using the SHA1 algorithm. If a piece sent by a peer matches our stored hash, we keep it. Otherwise, we discard it. So torrent files are serialized in a format called Bencode instead of JSON. The critical step is running a SHA1 hash over these raw Bencoded bytes to generate an info hash. Why raw bytes? Because even a single extra space could completely change the hash. So now let's understand how we do peer discovery. So the first method is tracker. Think of a tracker as a receptionist. Imagine walking into a hostel and asking who is staying in room 312. The receptionist doesn't give you the room key. They simply say Alice and Bob. Now you know whom to contact. A tracker works exactly like that. It maps an info hash to a list of peers, also known as a swan. The tracker then gives you their IP addresses so you know exactly whom to connect with. There are two types of trackers, TCP and UDP. TCP uses standard HTTP request and responses. It's reliable but requires a lot of back and forth conversation. UDP is much simpler. You connect, receive a ticket, announce yourself, and receive the peers. It's fast with no guarantees, making it perfect for tiny requests. But trackers have a fatal flaw. They can crash. If they go down, nobody can discover peers. We need a network that survives even if tracker disappear, which is why DHT was created. So how does a DHT work? Imagine trying to find someone's phone number. You ask a friend and they say, I don't know, but Alice might. Alice says, I don't know, Bob probably knows. And Bob finally gives you the answer. That's DHT. Nobody knows everything, but everyone knows a few nearby neighbors. So it's kind of like a graph. So in this system, every node has a 160-bit ID. Since SHA1 produces 160 bits, it perfectly matches our 160-bit info hash. To find peers, we use Kademlia logic, where the distance between nodes is calculated using the XOR operation. For example, between node A and target, a smaller number means that they are closer. If it is equal to 0, that means we have got the peer, which means this peer or this node has the piece. So this creates an iterative lookup process. You ask the closest DHT node you currently know. They might say, I don't have peers for this, but these three nodes are even closer to the hash. You ask those closer nodes and eventually you reach nodes that actually have the peer addresses for that torrent file. And then we use a bound. In our algorithm, we use a bounded version of this iterative lookup by repeatedly querying closed nodes and merging any newly discovered closer contacts. Finally, we run both the tracker and the DHT at the same time and deduplicate the results. Next, we open a TCP connection to start sending bytes. We initiate a BitTorrent handshake to confirm we are both using valid clients and are indeed talking about the same file. Once connected, we use a bit field to see which pieces each peer actually has. Think of it like this. If there are 6 pieces in total, we have a 6-bit sequence. 1 means I have the piece and 0 means I don't. So a bit field of 001001 means this peer has pieces 2 and 5. We keep track of the availability of every piece using counters. So we don't have to keep resending the entire bit field every time something changes. If a peer has a piece we need, we send an interested message. Then it's up to them to decide whether to unchoke us, meaning they'll start sending data, or choke us and refuse. Finally, we break each piece down into small manageable blocks and request them and assemble them back into the full piece. We verify that piece with SHA1, and if it checks out, we broadcast a have message to everyone so no one else wastes time sending us the same piece again. So now we need a piece manager. Its job is to make sure two workers never try to download the same piece at the same time. We handle this concurrency with a mutex. The manager tracks the global state of every piece. Is it pending, which means it's ready to download? Is it in progress? And if so, which worker owns it? Or is it completed and already verified? We assign one worker per peer to download concurrently using a mutex to prevent any race conditions. To decide which piece to grab next, we use a rarest-first algorithm, prioritizing pieces that are the hardest to find. But because we want to support streaming, we have to make a compromise. We force the first 15 pieces to download sequentially so the video can start immediately. But what happens if you drag the seek bar to jump from 0.15 to 130? We handle that with a priority override. We instantly mark the pieces needed for that timestamp as high priority, forcing the workers to switch focus. And for those rare moments when multiple pieces have the same low availability, we use uniform random tie breaking to decide which one to grab. So next, instead of mapping every single piece to its availability, we flip the logic. We use an availability to pieces bucket system. So we group pieces by how many peers have them. So to find the next piece, we just look at the first bucket. If it's empty, we check the second and so on. Why bother with this? A naive search is O times pieces, and sorting is every time takes OP log P. But what this bucket approach does, it is just O times bucket. And since the number of buckets is significantly smaller than the number of pieces, it becomes lightning fast. So we are using pigeonhole principle here. Now, supposedly you have an upload speed of only 4 Mbps and 100 peers connect to you at once. If you try to upload to everyone, you'll only giving each person 0.04 MB per second, which is basically unusable. So the first realization is that you cannot upload to everyone. Now, what happens if we share equally? A freeloader could upload nothing, yet still receive data from everyone else. If everyone starts doing that, the whole network would die. That's why we choke peers who don't contribute. The goal is simple. I reward the peers that help me. This is actually a classic concept from game theory, the iterated prisoner's dilemma, where repeated cooperation is the best long-term strategy. But what if you are a brand new peer? Everyone would just choke you and you'll never get a chance to start. To solve this, we use optimistic unchoking. We periodically unchoke a random peer just to see if they are a good partner. So here is the algorithm. We measure how well each peer performs, we rank them, we unchoke the top performers, and we keep the rest choked. And sometimes in every 30 seconds, we do optimistic unchoking as well. So now I'll just quickly go through the demo video. Hi guys, so this is the demo video for SiddTorrent. So as you can see here, we have a laptop where we can just upload the torrent file. So let's just select a file. I'll just use some test data file. Let's take Big Buck Bunny, and then we can just click on start download and it will start downloading. So as you can see in the DHT, it's already discovering. While it's discovering, I'll show you the control deck. These are the toggle pins which you can update based on your requirements. Let's see the torrents intel. So Big Buck Bunny has this size. This is the number of pieces, the info hash tracker, everything is mentioned here. And we can also see that our job is running. And as you saw, there's a new video player came. So basically this has been completed already. So in the video player, we can just click on it and you can see that it's completed, and we can actually run this whole audio file and it's working properly. So just for the copyright, I won't run this, but let me give you another example. So let's select another file, for example, let's say Sintel, right? And let's say start download. So now in my job matrix, we have got Sintel as well, and in the live session it's discovering and then it's gonna download it. So let's look at the live session in some more details here. So as you can see, it's connecting, it's connected to a few usable peers, and now it's gonna download the pieces. So as we can see, it's quickly downloading the pieces and they are getting downloaded in the download bar. Can we play the video while it's downloaded? Let's look at it. So this is a Sintel video, and stream is not ready yet because the pieces are getting downloaded. But when the pieces will be downloaded, we'll be able to play it. And as you can see, the stream is ready and we can actually play this. So that is the intuition behind this. And you can also play it in full screen and it's working properly. So that's the intuition. Yeah. And again, there is some issues because the pieces are getting downloaded. But yeah, you can at least stream the videos live and you can watch them all here as well. So I'm able to watch it within a laptop, inside the laptop, in a laptop, in a small screen. That's the intuition. That's pretty much it for SiddTorrent. Thank you.